So we start the second part of Chapter 4, Lesson 1, talking about linear and angular speed, and we start with the definition, the radian measure, which we started in 4.1. Radian measure is theta is equal to that arc length divided by radius. For a circle of radius r, a central angle theta intercepts an arc length of s, given by s equals, you can see we're just multiplying both sides of this equation by r. S is equal to theta times r, where theta is measured in radians. Note that if r equals 1, as we have talked about in our unit circle, then s is equal to theta, and the radian measure for theta equals the arc length. Let's look at example 5 and walk through that together. So in example 5, we're talking about a circle of radius 4 inches. We're going to find the length of the arc intercepted by a central angle of 240 degrees. So we have our circle. Radius r is equal to 4. So not the unit circle right now. We have to keep that in mind. To use our formula, we have s is equal to radius times theta. And we have an angle measure from here of, let's see, 270 is straight down. So 240, approximately 240 degrees. We're going to come around, create this angle. And what we'd like to figure out is that arc length all the way around to this terminal side, that measure s. So we're going to find that by using our formula. S is equal to radius, which we know to be 4, and before they did that, they converted our degrees to radians. So let's go ahead and do that. We understand 240 degrees, and we want to convert that to radians. That means we want to get rid of degrees, so we're going to place those in the denominator to cancel out, and we know that pi radians is equal to 180 degrees, and we're going to go ahead and do the computation here. Our units degrees cancel, and we end up with 240 pi over 180, and now we are in radians, and we get the measure 4/3 pi. 4/3 pi. Then using the radius 4, the arc length s is going to equal 4/3 pi times the radius 4, which gives us 16 pi over 3, and quick calculation gives us 16.76 inches. 2 hash marks for inches. Go ahead and try problem number 93, and we'll come right back here and look at that solution. So again, we're going to use our simple equation, arc length is equal to radius times theta in radians. So the first thing we want to do is take our 180 degrees and convert that by multiplying by our unit conversion factor. That's pi radians, equivalent to 180 degrees. And we know that degrees are going to cancel. We have 180 pi over 180, which gives us simply pi. We're going to plug that into our formula. Arc length is equal to radius, which they gave us as 14 units, and our radians, which we came up with as pi. We're going to do that multiplication. 14 times 3.14, roughly equivalent to 43.982 inches. So on a circle with radius of 14, we've taken out 180 degrees. We know that to be a half circle, or pi radians, multiplied by that radius, gave us 43.982 inches. So now what we'd like to do is take that information. We would like to start working on figuring out linear and angular speed. At the bottom of 259, we see the formula for the length of a circular arc. is used to analyze the motion of a particle moving at a constant speed along a circular path, or perhaps something we're familiar with, elliptical paths of planets, saw blades, tires on a bicycle. All of this applies. So if you follow along with me there at the bottom, we see a formula. Linear speed is equal to the arc length, of course the distance the particle has traveled, divided by time. So arc length we know to be s over time. So we're going to take that information that we just learned above in finding arc length and use it to find linear speed. The other thing that we're going to use this for, if theta is our angle in radian measure, corresponding to an arc length s, the angular speed of the particle, so we have linear speed and we have angular speed. Angular speed is going to be that central angle that is created by the particle traveling in a circle divided by time. And that central angle we know to be theta. Theta over time is angular speed, while arc length over time is linear speed. Linear speed measures how fast the particle moves. Angular speed measures how fast the angle is changing. So I'd like you to read example 6 with me, finding linear speed. We're looking at this clock radius from the central part of the angle to the outside. We have a radius of 10.2 centimeters, and it says the second hand is 10.2 centimeters long. Find the linear speed of the tip of this second hand. Well, right now we understand that second hand to make one revolution in 60 seconds. We know that already. And the s, our s, or arc length, is equal to 2 pi times the radius. 2 pi times our radius of 10.2 centimeters gives us about 20.4 pi centimeters. Well, that's the circumference we know in a complete revolution, 2 pi times radius. The time required for the second hand to travel, t equals 1 minute. So we're going to place that 1 minute, or in the form of 60 seconds. We want our speed in, I'm guessing they're doing centimeters per second. We're just going to do this quick calculation and find that we have a linear speed, that hand at the very tip, traveling around at 1 7/7 centimeters per second. So in example 7, it says find the angular and linear speed, and we have a 15-inch diameter tire on a car making 9.3 revolutions per second. Finding the angular speed, it says each of those 19.3 revolutions are going through an arc length 2 pi. That's one circle. In radians, one complete circle. So we can gather, that was supposed to be a 9.3 revolutions times 2 pi gives us that 18.6 pi radians per second. And that is our part A, finding the angular speed. It says the linear speed equal to arc length over time. That's radius times theta divided by time. We know that to be 1/2 of the diameter that they gave us times the distance, 18.6 pi, and we come out with 438.25 inches per second. Please try problem 109. Come right back here and we'll go over the solution. So problem 109, talking about a saw blade, a diameter of 7.5 inches, I believe. Yes, and 2,400 revolutions per minute. The first part, A, asks us for an angular speed. So we're going to take that measure theta over time. And here's what we know. We are 2,400 revolutions per minute. So that's 2,400 per 60 seconds, giving us 40 revolutions per second. So that's 40 revolutions, and in each revolution we are covering 2 pi distance. So 2 pi times 40 gives us 80 pi radians per second. And that is our angular speed. Part B says we want to find our linear speed. Now that's the arc length divided by time. The radius of the blade, 7.5. If we cut that in half, we get a radius equaling 3.75. And 3.75 divided by 12 gives us 0.3125 feet. Now our speed is equal to the arc length divided by time. We're going to take that radius, multiply or divide by time. We've got 0.3125 times our radians, which we got 80 pi in the previous part of the problem. 0.3125 feet, 80 pi times gives us 78.54 feet in 1 second. That seems like it's really moving. Go ahead now and look up your problem set on PowerSchool, and please ask any questions if you have them. Ready, set, go.